Hi everyone, welcome to our seventh lecture. This lecture is going to be on electricity, and it's a combined lecture for both the Calc and non-Calc based students. It's actually the beginning of a series of lectures which are going to be on both electricity and magnetism. And so in this lecture, I'm going to be talking specifically about electricity. In the next lecture, I'm going to be talking about electricity in circuits, that is voltage and currents and so on. And in the last lecture, I'll be talking about magnetism and the phenomena that it exhibits. Okay, and so the lecture we're going to watch was actually recorded last year at this time, and so I had to remove that introduction and replace it with this one. Okay. So what is electricity and magnetism? All right. Let's ask a more deeper question. What kind of forces are there, or what are the fundamental forces in the universe? And you remember last semester, I had to introduce forces because I introduced Newton's laws. Okay. And in Newton's law, you know, the second law being the most important, F is equal to ma, you have to know what a force is. And at that time, I told you that a force is anything that is a push or a pull. All right, so that's what a force is. But you could ask the question: can you kind of enumerate all the different forces in the universe? And we kind of did that when we were doing our problems. When we were drawing those free body diagrams, we would identify a frictional force, we would identify a normal force, gravity pulling down, and so on, tensions in strings and so on. And we were enumerating the forces, but if you want to enumerate them, you got to go all the way down to the microscopic level and say, what are these forces at the microscopic level, and are there fundamental forces in the universe? And the answer is yes. It turns out that there are four fundamental forces in the universe, and that the forces that we studied last semester, they were at the macroscopic level, meaning between objects that you could see and feel, which have about 1 mole of matter in them, like 10 to the 23 particles. But if you go right down to the microscopic, it turns out that both friction and the normal force, for instance, are both because of electricity and magnetism. Okay, and that's because the atoms are touching one another. When atoms touch, that touching is basically an electrostatic force between them. Okay, and so when you go right down to the microscopics and you study what causes these pushes or pulls, you discover that there's only four different types of forces that exist. Okay, well, the first one we did study in some detail, and that's gravity. And gravity is very important at the cosmological level because it's basically what holds planets together, it's what holds solar systems together, it's what holds galaxies together, and so on. And if there were no gravity, not only would you float away from the Earth, but the Earth itself would come apart, because what's holding the Earth together is like one part of the Earth gravitationally attracts another part of the Earth, and that causes all the pieces of the Earth that kind of like pull towards one another and makes a nice little ball. So if you turned off gravity, you would float away, but the Earth itself would kind of like start to fall apart because there'd be nothing holding it together. So planets are held together by gravity. The solar system is held together by gravity. The Earth orbits the sun because of gravity. The moon orbits the Earth because of gravity, and so on. Galaxies are held together by gravity, and so it's an important force at the cosmological level. It's the only force which is purely attractive. Okay, and that's actually why it's important at a cosmological level, because it's not like you can add more stuff and take away from the force of gravity. As you keep adding more matter, the force of gravity can only get more and more and more, because it's just adding like a bunch of positives. You cannot create anti-gravity. There's no such thing as anti-gravity, which would subtract away from gravity that's already there. So it just keeps building up, building up, building up. Okay, so that's the story with gravity. And the force that we're going to study in this section is electricity and magnetism. Okay, so electricity and magnetism, they are related, although at first they seem that they're not, and I'll show you that in a minute. But basically, this is the force which is responsible for holding matter together at the microscopic level. So if you have any solid material, uh, and you go down to the atomic level, well, there's a nucleus, and then these electrons are orbiting the nucleus. Okay, well, they're actually forming these standing waves because they're quantum mechanical particles. But at some kind of naive way, you can think about the electrons as orbiting the nucleus, and just like the sun keeps the Earth orbiting it because of gravity, the nucleus keeps the electrons orbiting because of the electrostatic forces. Okay, and So the atom is held together by electricity and magnetism, and then two atoms are stuck together. Say like H2, they're stuck together because of the covalent bond. That's also electricity, an electrostatic force, and then all the kinds of bonds that you have in organic chemistry. Those are all electricity and magnetism at play, and so on. And so basically, all of matter is built up. From the electrical force. And of course, if you've got a solid, then you have an entire lattice of atoms that extends right out to the macroscopic level. And if you see any solid object in your vicinity, well, that's because the atoms are all being held together by electricity and magnetism. Okay, and so there's the electrical force. It's much stronger than gravity, but it's not important cosmologically because it tends to cancel itself out. And again, I'll talk about that a little later when I talk about this phenomenon known as screening. Okay, so electricity is both attractive and repulsive, whereas gravity is only attractive. Okay, there are two other forces which I'll mention just for completeness. Um, because might as well talk about all of them, but we won't study them in the course. The next stronger one is the weak nuclear force. Even though it's called the weak nuclear force, it's stronger than electricity, but it's not as strong as the strong nuclear force. And it's responsible for things like the radioactive decay that occurs in materials where, like for instance in radiation therapy, where, some radioactive material will emit like fast traveling electrons known as beta particles, or fast traveling helium nuclei known as alpha particles, or else it'll emit gamma rays. Okay, and so this kind of force is basically due to the weak nuclear force. Okay, but then there's also the strong nuclear force. And the strong nuclear force, that's like atomic bombs or nuclear reactors, okay? The strong nuclear force is like responsible for even holding a proton together. The proton itself turns out to be made up of these three quarks, okay? And you wonder, why don't the quarks fly apart? Okay, well, that's because there's a strong nuclear force holding it together. And then the quarks also interact, the quarks with one proton even interact with the quarks of another proton. And as you'll see in a minute, positive things want to fly apart. And so a very natural question would be, why does the nucleus, which is made up of protons which are positive and neutrons which are neutral, why does it stay together? Like, why don't the two protons just fly apart in the nucleus? And the answer is because they're being attracted by a stronger force, the strong nuclear force. Okay, and so when you start breaking bonds at the strong nuclear force level, then we're talking like a tremendous amount of energy, and that's when you get like atomic explosions or nuclear reactors. A nuclear reactor is an atomic explosion which is being controlled very, very it's a very slow acting atomic explosion. A lot of heat is generated, and then you use that to make electricity. Okay, so there they are, the four fundamental forces. Again, if you look down at the microscopic levels deep enough, you discover that the universe has four fundamental forces. Gravity, which is the oddball because it's the one that's only attractive. Okay, then there's electricity and magnetism. Okay, magnetism turns out to be a kind of electricity, or is related to electricity, as we'll see later. And there's the weak nuclear force, and then there's the strong nuclear force. Okay, so let's let's compare electricity to gravity. Okay, so in gravity, the gravitational substance, that is the stuff that's responsible for causing gravitational attraction, is mass. Okay, and mass only comes in one variety, positive. Okay, so you say this thing has a mass of 5 kilograms, or that thing has a mass of 7 kilograms, and there's no such thing as negative mass. Okay, you don't have like negative 5 kilograms. That's nonsense. Okay, it's like as soon as there's something there, it has positive mass associated with it. Okay, and any two masses, like there I have drawn that 7 kilogram blob and the 5 kilogram blob, they attract one another. Okay, so these positive masses, they only attract one another. Okay, and there's the story with gravity. Okay, now with electricity, the electrical substance, the thing that's responsible for causing the electrical force, is called charge. Okay, and it comes in two varieties, and we could have called them whatever, but we tend to call we've chosen the names positive and negative. We could have chosen the names red and blue or something like that. Okay, they're just two different varieties, and we call them positive and negative. Okay, and so for example, you can have a charge which is plus 5 coulombs. We'll talk about what a coulomb is in a bit. Okay, so plus 5, or you can have another charge which is negative 7 coulombs. Okay, and so you can have either positive or negative charges. All right, and it's both an attractive and a repulsive force. Okay, and the way this works is like charges will repel and opposite charges will attract. Okay, so if you have a situation like this where you have two positives, the two positives will repel one another. Two negatives, they will also repel one another. Okay, so like charges will repel, but a positive and negative, they will attract. All right. And so there you go. This business of having these two different types of substances which carry electricity, that's just a property of electricity, of the electrical force. When it comes to something like the strong nuclear forces, it turns out that there are three charges, and we couldn't call them positive and negative. We call them red, green, and blue. Okay, and then there's also anti-red, anti-green, and anti-blue. And so this choice of positive and negative was kind of I wouldn't say arbitrary because it was inspired by mathematics, but we didn't there's nothing plus about the positive charges, as we chose to call it that. Okay, so uh, um, let's get to this idea of screening. Whoops, I scrolled too far. Let's get to this idea of screening. Even though gravity is the weakest force in the universe, it turns out that it's really what holds the universe together. Okay, and that's because, as I mentioned earlier, gravity only adds up. It only leads to attractive, and it's more attractive and more attractive. The more matter is there, the more attractive it becomes. And so what I have here is, a picture of just a bunch of masses here. Okay, these asteroids, whatever. Okay, out in space. Okay, and here we have maybe another asteroid, and these arrows here, those are basically the forces of attraction. It feels attracted to this mass. It feels this mass here feels attracted to that mass. It feels attracted to that mass, that mass, that mass. It feels attracted to all of them. So if you were to add up all those forces, the net effect would be to pull this mass in towards these other masses. Okay, whereas with electricity, you can have positives and negatives. And most matter is made up of approximately the same number of positives and negatives, okay? Because the electrical force is so strong, if you had way too many negatives or way too many positives, you'll actually blast the material apart. Okay, like if you put enough static electricity on something, the material itself will break apart because the negative, say you added a bunch of electrons, they'll just want to fly off in different directions. If that force gets big enough, it'll tear the matter apart. So most ordinary matter is made up of approximately the same number of positives and negatives. It might have a little bit more negative, in which case it's negatively charged, or maybe a little bit more positives, in which case it's positively charged, but roughly speaking, approximately the same number. Okay, so over here we have ordinary matter, and you can see here I have three positives in this ordinary matter and three negatives. Okay, and now here's a positive charge. It's sitting nearby, and it feels attracted to the negatives. Okay, so I got three arrows here showing that the positives being attracted to these three negative charges, but at the same time it's being repelled by the three positive charges. And so does this charge get attracted or repelled? And the answer is both. Okay, with a net effect that the charge doesn't really either get attracted or repelled from this blob of charges over here. Okay, and so because electricity has both attraction and repulsion over a distance, it tends to just cancel out, because a charge will just see as many positives around it and as many negatives, and it goes, well, I feel kind of neutral here. I don't feel like being pulled one way or the other. And so the electrical force, even though it's much stronger than gravity, will tend to cancel out, whereas gravity only builds up. And so that's why you're not going to have an electrical force holding planets in place. It's going to be gravity. Okay, so this effect, by the way, is known as screening. And you might wonder, why is it called that? Well, just because if you think of if you've got like a charge out here and a charge here, and you've got a whole bunch of positives and negatives in between, well then the any kind of attraction or repulsion between the two charges is basically screened by all the other positives and negatives around it. Okay, and so there you go. It kind of cancels out. As a result, it's not that the force isn't there. It's just that over large distances it tends to be screened out. But over short distances, it's pretty strong, and that's exactly what touching is. Okay, so yeah, gravity is pulling me down into the earth, but I'm sitting on my couch here. It's pushing me up, and at the short distances of touching, yeah, those electrical forces start to really build in, okay? Because then you're no longer really screening. You've got the electrons of one atom pushing up against the electrons of another atom, and the repulsive forces start to kick in, okay? So there's just a kind of a brief qualitative description of the difference between gravity and electricity. Let's look at the differences between electricity and magnetism. Now, at this point, I'm going to kind of try to convince you that they're different, but it'll turn out towards the end of this section that magnetism really is electricity in disguise. Okay, and it was really Einstein who really teased that one out very well with his theory of special relativity. We won't go that far, but I'm going to give you all the experiments that led up to Einstein's understanding. Okay, so electricity and magnetism, they really are the same fundamental force. Okay, although on the surface they don't seem to be. Okay. So I mentioned that electrical substance comes in both positive and negative, okay? And you say, well, is there an equivalent for magnetic substance? And the answer is yes, it comes in north and south poles, okay? And hopefully you've played with magnets as a kid. If not, well, go get a compass and a magnet and play with them. They're always a lot of fun. And the north and south poles, they act just like positive and negative in this sense. Like poles will repel, and opposite poles will attract. Okay, so basically, kind of similar to the diagram I had above, but now I put a north pole of a magnet near the north pole of another magnet, they'll repel. Okay, or I put the south pole of a magnet near the south pole of another magnet, they'll also repel. Okay, but if I put the north and the south together like that, then they're attractive. Okay, and so you're starting to think, well, maybe north is maybe just positive. Maybe we overnamed this. Maybe the north pole of a magnet is like positive, and the south pole is negative. Okay, north positive and south negative. Is that it? Is that what's going on here? And the answer is actually no. They are quite different. Okay, and there's two experiments. There's probably more, but just two experiments that I could easily describe to you to prove to you that north and south are not positive or negative. Okay, so the first is if you just take north, it's neither attracted nor repelled by a negative charge. Okay, so you could have a north pole and you bring a negative charge or a positive charge near it, and it doesn't attract or repel it. And it's the same thing with the south pole. The south pole is neither attracted nor repelled by a charge. Okay, and so you could do this very simple experiment here. So basically you take a magnet and you allow it to swivel through the middle, and by the way, as soon as you take a magnet and you allow it to swivel through the middle, you've got what's called a compass. Okay, because it'll point to the north pole here will point towards the north pole of the earth. Okay, and you bring a positive charge, and you can move that positive charge near the north and near the south here like that, and the magnet goes, I don't care. But if you were to take a magnet and put it near the north or the south here, boy, that needle will flip around pretty quickly. Okay, and so the positive charge doesn't affect the compass at all. And I pick positive, but you could do it with a negative, and it would also make no difference at all. Okay, and so yeah, it's there. This experiment itself would be sufficient to show you that they are actually not the same. Okay, now another experiment that you can do is you could try to separate north and south and try to separate positive and negative, and you'll discover something really interesting. Okay, you cannot separate north and south. All right, and you say, well, can't I just break a magnet in half? Yes, you can break a magnet in half, and here I've got a picture of a magnet north and south, and here you can see the squiggly line. I'm going to break that magnet in half, and you know what I get? Two magnets, both of them with a north-south pair. Okay, so you can't separate a north-south pair. If there's a north somewhere nearby, there's a south. Okay, so north and south always come paired together. Okay, now with charges, yes, you can separate them. So like here I have a positive and a negative. We could go right down to the microscopic level. So say this is a hydrogen atom. Okay, so a hydrogen atom is made up of one proton and one electron. And can you ionize a hydrogen atom? That is, can you take that electron, which is orbiting this proton, just kick it out and leave the bare proton there, and then the electron is flying off? The answer is yes. Okay, so poles cannot be separated, whereas charges can be separated. Okay, and so it appears at this level, at least so far, that electricity and magnetism are different forces. But like I said, later they will turn out to be the same. Okay, just one last thing I'm going to mention. It's not really part of the physics of this, but just a kind of a curiosity about how compasses work. So north is attracted to south. Okay, that means that the north pole of a compass is attracted to the south pole of the earth, but it points north. And you know why? Because our geographical north, like our north pole, is actually a south pole magnet. Okay, so that's a little bit weird. You may not have heard of that before, but yeah, north pole, that is north of Canada, that's our geographical north, but it attracts the north of a compass. And so the north of a compass here is actually attracted towards the south pole of the Earth, the south magnetic pole of the Earth, which is actually our geographical North Pole. Okay, so I won't say much more about that, but it's just kind of a curiosity. You might say, well, if north is attracted to south, then why does the north pole of our compass point towards the north pole of the Earth? Shouldn't it point towards the south pole of the Earth? And the answer is it does. It's just that the geographical north pole is actually a magnetic south pole. Okay, so a little bit of a curiosity there. All right, let's go on. Now, electricity has been studied a lot, and it's got a very interesting history, like how a lot of the stuff was discovered. I'm going to skip a lot of that detail just because we don't have time in this course. But one of the major players in that game was Coulomb. Okay, he was a French physicist, and he basically was able to take metal balls and create charges on them, put static charges on them. Static charges just means charges which are not moving. Okay, so you'll hear me say static electricity a lot, and you're wondering, why am I saying static electricity and not electricity? This is basically electricity which is not flowing. Okay, later on in the course, when we have electricity that flows, that'll be called a current. Okay, so anyhow, back to Coulomb. He would have these balls, and he would look and put them together, and he was able to control how much charge you would have on them. Okay, and he would be able to bring them together and say, oh, look at how much force is between them. Okay, and so by knowing how much charge was on the balls and how close they were together and the forces of repulsion or attraction, he came up with Coulomb's law. And here it is. Here's Coulomb's law. So what does it say? The force between two charges Q1 and Q2, so you have these two charges Q1 and Q2, okay, and they're a distance r apart, and there's going to be a force, an electrical force between them, F, and that force is given by F is equal to K, Q1, Q2 over R squared. Okay, now what's K here? K is Coulomb's constant. Okay, and like Q1 is going to be measured in some units called coulombs, Q2 is going to be measured in coulombs, M is going to be measured in meters, and what we want coming out of this is a force in newtons, and so you got to have some number there that makes sure that all the units work out right. Okay, and this is known as Coulomb's constant. There it is. K is equal to 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Okay, now at this point you might say, well, what the heck is a Coulomb? Well, in doing his work, Coulomb came up with units of charge, and the unit of charge today is called a Coulomb. Okay, and you'll see how many electrons that is in just a minute, but basically a Coulomb turns out to be an extremely big unit for charge. Okay, so if you're like walking across carpeting and you get a little bit of static electricity, and you go to touch a doorknob and you feel that static electricity, the little zap that you get with the door, that's nowhere near a Coulomb. In fact, those kinds of charges are typically in the microcoulomb range. Okay, and remember that micro is 10 to the minus 6, so we're talking millionths of a Coulomb. All right, so those little sparks are in the millionths of a Coulomb. For an entire Coulomb, I mean, you're talking about lightning or something very serious like that. Okay, so there we go. There's Coulomb's law, and let's do a simple example with it. We're not going to do a lot of problems with Coulomb's law because, generally speaking, we're not that interested in just isolated charges. We're going to be more interested in charges that build up certain configurations. as you'll see. Okay, so here we have an example where I have a 7 Coulomb charge, and it's placed 5 centimeters from a 3 Coulomb charge. Both of them are positive, and I ask two questions: is the force attractive or repulsive, and how big is the force? Okay, well, the first thing is, and I put the pluses in front to emphasize this, they're both positive charges, and positive and positive, they repel. Okay, so the force is repulsive. All right, and I wouldn't try to put signs inside of Coulomb's law or anything like that. What I would do is I would, just by looking at the signs of the two charges, determine whether it's attractive or repulsive. Okay, so over here, how big is the force? In other words, what's its magnitude? So F is equal to K Q1 Q2 over R squared. And so here's Coulomb's law. And here is the first charge, and it's 7 microcoulombs. So that's 7 times 10 to the minus 6 coulombs, and then 3 times 10 to the minus 6 coulombs divided by 5 centimeters. Convert that to meters is 0.05 meters. Crunch that through your calculator, and you get that it's 75 newtons. Okay, so 75 newtons, that's quite a bit of force. That's quite a bit of force between like a 7 microcoulomb charge and a 5 microcoulomb charge that are 5 centimeters apart. Okay, and so yeah, even a microcoulomb is big enough. It's big enough. That's a substantial force there. Okay, so let's go on here. Now, how big? Like, you want maybe an idea or a sense of like how big a coulomb is, and the smallest unit of charge in the universe is basically an electron. Okay, and well, there's some qualifications to that, but like electricity. For the purposes of this course, electricity, it comes in discrete bundles, and the smallest discrete bundle is basically an electron or a proton. And an electron has the same amount of charge as a proton. It's just that one is negative, the electron is negative, and the proton is positive. Okay, and so like you either have a charge of 0, or you have a charge of 1 electron or 2 electrons or 3 electrons. You're not going to have a charge of like half an electron. Okay, that doesn't happen. All right, so if you have something like plus 7 microcoulombs, that represents a deficit of electrons in a material. Okay, it's like you've taken out some of the electrons. Okay, and so you can naturally ask the question, how many electrons did you have to take out of this material in order to charge it to the point that it has a 7 microcoulomb charge? By the way, you might say to yourself, well, why are you taking the electrons out? Why not just add protons to the material? Because if you add protons to the material, you'll also make it positively charged. Okay, so you can make it positively charged by adding protons or by removing electrons. And the answer is the electrons are the fluffy things that flow. Okay, so an atom is made up of a nucleus, which is very, very heavy, and the electrons, which are on the outside, and they're very, very light. Okay, roughly speaking, an electron is only 1/2000th the mass of a proton. It's actually 100 and 1,800 and something, but just rounding it off, it's like 1/2000th of the mass of a proton. So you could see that the protons and the neutrons are very heavy, and these electrons are fluff. So they're the ones that actually tend to do the flowing. They're the things that get removed from material or added to a material to charge it up. Okay, so it turns out that the charge of 1 electron is minus 1.6 times 10 to the minus 19 coulombs. Okay, that was actually measured by Millikan a little over 100 years ago. Okay, so 1 electron, it's negatively charged, so you can see the negative sign there, 1.6 times 10 to the minus 19 coulombs. Okay, and so the number of electrons you're going to have is basically the full charge, which is that 7 microcoulombs, or 7 times 10 to the minus 6, divided by the charge of just 1 electron, 1.6 times 10 to the minus 19, and that turns out to be 4.38 times 10 to the 13 electrons. Okay, now that looks like a big number, but it's actually not a big number at all. Okay, so that's the number of electrons that you would actually have to remove from material to charge it up to 7 microcoulombs. But it's not a lot of electrons. And you go, well, 10 to the 13, that sounds like a lot to me. Okay, no, because most macroscopic materials are made up of approximately a mole of matter. okay, roughly speaking. In other words, like if if you have some object in your hand and you say, how many particles are in this object? Well, you don't know exactly, but you know the order of magnitude. It's going to be roughly 10 to the 23. If it's a small object, maybe 10 to the 22 particles. If it's a big object, maybe 10 to the 24, but roughly in the 10 to the 23 particle region, okay? And I'm thinking of Avogadro's number here, 6 times 10 to the 23, okay? So macroscopic objects are about 10 to the 23, but this is down at 10 to the 13, okay? And that's 10 orders of magnitude difference, okay? That's like 1/10 billionth of a mole, all right? And so all you're basically doing to get that 7 microcoulomb charge is taking out 1 electron out of every 10 billion atoms, okay? And so it doesn't take a lot to create a significant charge, and this gives you a sense of just how strong electricity is, okay? Most matter is very close to being charge neutral. In other words, count the number of protons, count the number of electrons, they're equal. Okay, and that gives you charge neutrality. If you were to pull out even 1 electron out of every 10 billion atoms, then you've got a 7 microcoulomb charge, and that's enough that if you put it beside that, like in the previous example, that 3 microcoulomb charge, at even a 5 centimeter distance, you've got 75 newtons of force. So electricity is pretty darn strong. It's a strong force. Okay, all right, and one more thing to note before we go on to the next subject. If you were looking carefully here, you would have noticed that Coulomb's law looks a lot like another law that we've seen earlier last semester. And you can actually compare Coulomb's law to Newton's universal gravitational law. Okay, and so here I have them both side by side. Oh, I lost the. I'm sorry about that. Okay, here I have them both side by side, okay? So here's Coulomb's law, F is equal to K, Q1, Q2 over R squared. And here's Newton's universal gravitational law. So remember, between any two masses in the universe, M1 and M2, there's going to be a force of gravity given by F is equal to G, M1, M2 over R squared, okay? They look very similar, except that where you have masses with Newton's universal gravitational law, you have charges with Coulomb. Understandably so, because masses cause gravity, whereas charges cause electricity. Okay, they're both inverse R squared laws. Okay, and we actually saw that with intensity with sound. Okay, a lot of things follow this inverse R squared law. All right, and there we go. All right, and they both have a constant, but of course the constants are different because we're trying to match different units here. This is G, and if you remember from last semester, that's the universal gravitational law, gravitational constant, and this is K, which is Coulomb's constant. Okay, and you can actually compare the sizes of the two, and you can see that Coulomb's constant is 8.99 times 10 to the plus 9 Newton meter squared per Coulomb squared, whereas Newton's universal gravitational constant is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Okay, now this one, Coulomb's constant, is much bigger than Newton's gravitational constant by many orders of magnitude. Okay, like this is plus 9 and that's negative 11. Okay, so this is a very tiny number and that's a very big number. All right, it is a bit of comparing apples and oranges, because like how big is a Coulomb versus how big is a kilogram, and a kilogram, a kilogram of stuff is approximately the the amount of stuff that you have like at the macroscopic level, whereas a Coulomb is pretty big. Okay, it's probably 1,000,000 times bigger than ordinary charges that you have at the macroscopic level. But nonetheless, you've got this huge difference in orders of magnitude, and that's because, again, the electrical force is much larger than the gravitational force. Okay. All right. Next topic. Okay, electric field. All right, so let me give you the definition of an electric field first, and then try to tell you why it's kind of an interesting idea. Basically, an electric field is defined as the force at some point in space divided by the amount of charge at that point in space. So it's basically the amount of force you get per unit charge. Okay, now why is this an interesting idea? to motivate that, I'm actually going to compare it to gravity, gravitational field, which is G. And here for the electric field, okay, you can write this equation right here. All right, so the amount of force that you get at a particular point in space, so you pick a point in space, okay, you pick a point in space and you say, what's the electrical field there? E. And you say, okay, I'm going to put a charge Q at that point in space, Q, and if you multiply Q times E together, you get the amount of force that that electric field is exerting on that charge Q. Okay, so F is equal to QE is a formula that we'll be using to relate the force on a charged particle in an electric field E. And this formula here should look kind of familiar because you can draw a direct analogy to masses in a gravitational field. So if you've got a mass M, okay, right here, you got this mass M, and you put it in a gravitational field that is G, little g, 9.8 meters per second squared, well, then there's a force on it, okay? And you could say the force of the force on a mass M in a gravitational field G is equal to F is equal to mg, okay? And so let me try to put both of these together. Okay, so here you've got from last semester F is equal to mg. All right, so a mass M in a gravitational field G gives you a force F. Here, the analogous idea is a charge Q in an electric field E gives you a force F. Okay, so the way you can think about this is, here's the gravitational example. So everywhere in space, there's this gravitational field. You can't see it. And you go, well, how do I know it's there? The only way you're going to know it's there is if you put a mass M at a particular point in space. Every point in space has like a little vector attached to it, G. This vector has a magnitude of 9.8 meters per second squared, and it always points down. Every point in space has this vector G pointing down, okay? I'd be really weird if there were this pocket of space which didn't have any gravitational field in it, because if you put a mass into that point, it would experience no gravitational force, because no gravitational field, no gravitational force. But everywhere at the surface of the Earth, you could say at every single point here, it's like this point here has a vector G, and it points down, and its magnitude is 9.8 meters per second squared, okay? So you don't see the field, but if you put a mass M in there, so here I'm going to put this mass M in my gravitational field, ta-da, that mass M experiences a force F due to that gravitational field. Okay, so that's the gravity way of thinking about it. For electricity, you can do the same thing. But now what you need to do is, whoops, let me just scroll down a bit here. What you do is you basically create these two parallel plates here, and you charge them. Okay, so you could do this with metal plates. So here you could think of this as a metal plate, and here's a metal plate here like that. And using a battery or whatever technique you like, you're going to pull electrons out of the top plate, making it positively charged. And you're going to add electrons to the bottom plate, making it negatively charged. Okay, and then in this region between these two plates, you've essentially established an electric field. And you go, well, how do I know there's an electric field there? Well, just like in the gravitational field, you find out that there's a field there by putting a mass. In the case of the gravitational field, for electricity, you put a charge. And so here I am. I'm going to put this charge Q in the middle of my electric field. It's called a test charge because that's exactly what you're using it for. You're testing for the presence of an electric field. So you put this positive charge in here and you say to it, well, what force is on it? Well, let's think about this for a minute. Okay, so you've got all these positive charges up here, and they are repelling the positive charge. Okay, so the positive charge here is being repelled by all of these positive charges up here. And the negative charges down here, they're all attracting the positive charge. And so the positive charge feels repulsion from above and attraction from below. And you've got all these different vectors here, okay? And there's some vectors which are to the right, have a little bit of a right component to the right. There's some vectors which have a little bit of a component to the left. But because of the symmetry, if you were to break this down, each of these vectors into a vertical component and a horizontal component, all of the horizontal components would cancel out. And that's because there's as many components to the left as there are components to the right. And all your right components will cancel all your left components, and basically there would be no horizontal force on this charged particle. Okay. However, all of these vectors have a downwards component to them. Okay, none of them have an upwards component. It's being repelled by the top plate and attracted to the bottom plate. And essentially what that means is that you get a force on this charged particle, which is downwards. Okay, so here's that charged particle Q, positive, and there's going to be a force downwards away from the positive plate and towards the negative plate, purely downwards. And if you move this test charge everywhere in between these two parallel plates, you would find that at every point in space, the electric field is pointing down, away from the positive towards the negative. Okay, and so you've got that. Only on the edges does the electric field kind of fray out. Okay, so I did draw the the electric field kind of like bulging out at the edges here like that, but everywhere in the middle of these parallel plates, the horizontal components of the forces are all going to cancel, and the symmetry is going to insist that the electric force be purely down. As you can see here, my F is purely down. Okay, and that means that the electric field is purely down. And the other thing is, now I'm not going to do a full analysis of this. It actually requires vector calculus to do it. But if you were to do a proper analysis of this, you would find that not only is the electric field always pointing down in this region of space, that is the region between the two parallel plates, it's always constant. So the electric field is a constant downwards value all the way through here. Okay, and again, I can't really prove that very easily, not even for Physics 102, but it does turn out to be that. So in a sense, these parallel plates is exactly the electrical equivalent to gravitational field at the surface of the Earth, because a gravitational field at the surface of the Earth is a constant gravitational pull down of 9.8 meters per second squared, and the electric field between these two plates is a constant E. Now, E might be different depending on the plates, but it's a constant value of E. It's a constant magnitude of E, always pointing from the positive to the negative plate. Okay, so I think you can see the analogy between gravity at the surface of the Earth and the electric field between two parallel plates. So electric fields are very useful this way. They're very useful in terms of picturing what would happen if you put a charged particle at a particular point in that space. Okay, and I don't want you to think that the electric field is going to be always up and down the way the gravitational field is. In my previous diagrams, I did it that way to try to hammer home the analogy between gravity, which is downwards, and the electric field. But no, the electric field is always from basically the positive plate to the negative plate, no matter what the orientation is. Okay, so they are different forces, and there it is. Okay, so electric field, if the plates were oriented vertically this way, and you've got positive on this side and negative there, you would have an electric field pointing from the positive plate to the negative plate. Okay, so before we do a problem, let's ask the question, what are the units of the electric field? And if you rearrange the force F is equal to QE to E is equal to F over Q, the units of force are newtons, and the units of charge are coulombs, and so the electric field has units of newtons per coulomb. Okay, basically it's telling you how many newtons of force do you get for every coulomb of charge that you put at a particular point in space. So I picked this point, I put, I don't know, 3 coulombs there. How many newtons of force do I get? Say 3 newtons of force. So if I got 3 newtons of force on 3 coulombs, that's going to be 1 newton per coulomb of force for every for the charge that I put at that point in space. Okay, all right, so let's do a problem. And this problem was actually inspired by what's known as the Millikan oil drop experiment. And that was the experiment that Millikan did many years ago, about 100 years ago, to actually determine how big the charge of an electron was, what the charge of an electron was. Okay, and so here, during a thunderstorm, the electric field between the Earth and the clouds is found to be 100 newtons per coulomb. Okay, and this is sufficient to keep a drop of water with a mass of 0.1 grams from falling. So here's this drop of water, and of course gravity wants to pull it down, but the electric field is pushing it up, and it doesn't want to fall. It's not going to fall. The electric field keeps it from falling, and the droplet just remain suspended. In fact, if the electric field were stronger, then the droplet would go up, okay? But no, the electric field is just strong enough to keep that droplet suspended in space, okay? And I want to know what's the charge on the drop, okay? So let's calculate that, okay? Now, we don't know, I didn't tell you in the problem whether the electric field was pointing up or down. I didn't say if the ground was positively charged or the clouds are positively charged. So, you know, we won't worry about that, but we can calculate the charge, okay? And basically what you have to have in this situation is the force of gravity up has to be exactly balanced by the electrical force up has to be exactly balanced by the force of gravity down, okay? And since the droplet is suspended, these two have to be equal to one another. Okay, so the electrical force, that's equal to QE, and the gravitational force, that's equal to mg. We're solving for q, so we could just rewrite this as q is equal to mg over e, like that. And plugging in the numbers, the mass here, the mass of the droplet was 0.1 grams, but we have to convert to kilograms, so it's 0.1 times 10 to the minus 3 kilograms. G, I'm just going to round off to 10 meters per second squared. And E, I told you in the problem that it's 100 newtons per coulomb. All of these units are in MKS, and so this works out to 1 times 10 to the minus 5 coulombs. Okay, so this is a small charge, all right, but let's convert it to actually number of electrons, just to give an idea of like how many electrons you would have to either add or remove from the droplet in order to get the charge, sufficient charge, so that it remains suspended in this electric field. Okay, and so the number of electrons is going to be equal to the total charge divided by the charge of one electron, and there's the charge of one electron. Okay, so one electron has a charge of 1.6 times 10 to the minus 19 coulombs. If you divide that, you're going to get this number here, 0.625 times 10 to the 14 electrons. Okay, so again, this is either a deficit or a surplus. I'm not sure which because I didn't tell you, but there it is. Okay, now that's actually quite a lot of electrons, and I wonder if such a droplet is even possible, because with that many electrons on a tiny little droplet, it might be enough to actually, you know, tear the droplet apart. Okay, so I don't know, but you know, that is the correct answer there. Okay, so that's one problem. Here's another problem with electric fields. What's the acceleration of an electron in a 10,000 Newton per Coulomb field? Okay, and so if you put an electron inside of an electric field and you let go, that electron is going to start to accelerate. It's going to accelerate away from the negative plate, and it's going to accelerate towards the positive plate. And I might want to know, how much is this electron going to be accelerating? Okay, so well, let's figure out the force on the electron first, because the force is equal to QE. And Q, the charge of an electron, is 1.6 times 10 to the minus 19. I'm not worried about the sign here. Yes, I know it is a negative 1.6, but I'm only worried about the magnitude of the force. Okay, so I'm not worried about the direction. I know it's going to be away from the negative plate towards the positive plate. So if you're wondering why did I drop the negative sign, that's why. Okay, and so I got 1.6 times 10 to the 19 coulombs, and the electric field is 10,000 newtons per coulomb, or 10 to the 4 newtons per coulomb, and that gives me a force of 1.6 times 10 to the minus 15 newtons. Okay, that is a very tiny force, but electrons are very tiny. Okay, so the charge of an electron is 1.6 times 10 to the minus 19. What's the mass? All right, and I did tell you that they are very, very light. So here we go. So now that we have the force, and we're going to look up the mass, we can calculate the acceleration. So the acceleration is just the force divided by the mass. And it turns out that the mass of an electron is 9.11 times 10 to the minus 31 kilograms. Okay, so if you remember, the mass of a proton was like 1.66 times 10 to the minus 27, and this is minus 31. So we're talking between minus 27 and minus 31. That's 4 orders of magnitude. Okay, so that is significantly electrons are significantly smaller than protons. Okay, so if we plug that in here, we get that the, whoops, I made a mistake. Sorry, guys, that should be A there. So you see where I have F there? That should be an A, okay? So A is equal to 1.6 times 10 to the minus 15 divided by the mass. and you get that the acceleration on the electron is 1.76 times 10 to the 15 meters per second squared. Okay, so again, I apologize, that F there, right there, that should be an A, because A is meters per second squared. So the acceleration is 1.76 times 10 to the 15 meters per second squared. And I put a wow beside there because the acceleration due to gravity is 10 meters per second squared. That's like 10 to the 1. And this is like 10 to the 15. So this is huge. And by the way, it's not at all hard in the lab to produce 10,000 newtons per Coulomb electric field. Okay. In fact, in my example later, you'll see how to do that with a battery. All right. So there we go. There's the story with electric fields. Basically, just to summarize, there's a series of charges that create an electric field. That would be like the charges on the plates. Okay. And all the space around those charges and between those charges has an electric field. If you put a test charge inside of that electric field, it's going to have a force, and the force on that charge is going to equal to Q times E, where E is the electric field. So F is equal to QE. All right. And it's very much analogous. Electric field is very much analogous to G in gravity. All right. So the next topic is going to be electrical potential energy and electrical potential. Now, these two are sometimes confused because the names are very similar, but the first is electrical potential energy, and the second one is electrical potential, okay, or voltage. All right. So the electrical potential energy is basically the equivalent of gravitational potential energy, okay? But the electrical potential energy is due to the charges, configuration of the charges, whereas gravitational potential energy is due to the configuration of the masses, okay? Now, electrical potential, which is also called voltage, it's not really the potential energy, it's the potential energy per unit charge that you place at a particular point in space, okay? And so so voltage is going to be the potential energy divided by the charge. All right, so let's see how that works. And again, to get the idea straight in our head, we're actually going to do gravity and compare it to electricity. So with gravity, you know, near the surface of the Earth, you have this gravitational field here, like that. Okay, and it's uniform gravitational field, and you have a mass m, and it's at some height h, like that. Okay, so the gravitational potential energy of this, I'm going to give it the symbol U here. I think last semester I just called it PE, but I'm going to give it U, and it's going to be a subscript G because this is the gravitational potential energy. It's equal to the mass. The bigger the mass, the more gravitational potential energy you get. It's equal to the size of the field, G, and it's equal to H, that is how far into the field the mass has been moved. Okay, so this idea of like moving into a field and gaining energy as you move into a field, that's a little bit different than the way we thought about it last semester, but we should start thinking about it now. You can think about the mass at the ground here. If the mass is at the ground, it's got no potential energy. As I lift the mass, what am I doing? I'm moving it into the field. I'm moving it into the field. If I move it into the field H, a distance H, then the gravitational potential energy is equal to mgh, like that. Okay, so great. So there's the story with gravity. What about electricity? Well, the equivalent of a uniform gravitational field in electricity is the parallel plate. So here we go. We've got a positive plate on top and a negative plate on the bottom. Again, the orientation, I just put them this way so that the analogy is obvious, but you know, it doesn't matter what the orientation of the plates are. Okay, and so inside between these two plates there is a uniform electric field. Okay, and it's always pointing from the positive towards the negative, like that. All right, and the charge here has a charge Q. All right, and I've moved it, I've displaced it into the field a distance h. Now think about this. This is a charge Q, and so this charge Q, where would it like to sit? It would like to sit right here on the negative plate because it's being repelled away from the positive plates and being attracted to the negative plates. Okay, so you know, if I were to just sort of place that positive charge right here on the negative plate, it would say, I'm happy here. Leave me alone, you know, I'm fine. Now, if I take it and I lift it, it wants to fall back down. If I take it and I lift it a distance h into the field, okay, then as I'm lifting it into the field, as I'm pulling this charge Q into the field, then I'm giving it potential energy. And if I've pulled it into the field a distance h, then the potential energy that this charge has is equal to QEH, okay? And so, a charge Q, the bigger the charge Q, the more potential energy it has. The bigger the field, the more potential energy it has. And the more I've pulled this charge H into the field, the bigger the potential energy is. Okay. Now, I've been working a lot with positive charges, and that's kind of traditional in this field to just work with positive charges. But let's think about what would happen with a negative charge, okay? Let's keep the positive plate on top and the negative plate on the bottom. For negative charges, and I've got a problem for this later, okay? For negative charges, it's kind of like this whole picture gets flipped upside down. So if a negative charge were in here, it would actually want to sit up here at the positive plate, okay? And then with a negative charge, as you pull it into the field, it would gain potential energy. And if you let go, it would want to fall back up that way, okay? And so over here, this potential energy, it's being measured to the negative plate because that's where the positive charge wants to go. The positive charge wants to go to the negative plate. But if I had a negative charge in there, then that H would actually be measured towards the positive plate because it wants to fall towards the positive plate, okay? There was no equivalent of that with gravity because gravity is purely attractive, and so there was only one way, down. But over here, if I put a charge in here, if it's a positive charge, it falls down. That is, it's attracted to the negative plate. But if I put a negative charge in there, it's flipped. It gets actually attracted towards the positive plate and it falls up. Okay, so just keep that in mind because in a lot of my examples, as I'm presenting the theory, I'm going to be thinking about putting a positive charge in there. But in general, like we could be doing this also with negative charges. And just to make the similarity explicit here, the gravitational potential energy and the electrical potential energy, they're quite synonymous. If you take mass and replace it with Q, you go from gravity to electricity. If you take G, which remember was the measure of the gravitational field, okay, at the surface of the Earth, G, and you replace it with E, then again you're going from gravitational potential energy to electrical potential energy, and it's H in both of them. Okay, it's H because it's the distance in which you've pulled the object into the field. Okay. Now, everything I talked about up to this point was electrical potential energy. Let me now define for you electrical potential. Okay, so electrical potential is given the symbol V, and it's equal to the potential energy per unit charge. Okay, so it's like the potential energy divided by Q. Okay, now this is a general definition and it's used everywhere, but like unless you want to start pulling out vector calculus, the easiest place where you can actually apply this is to the parallel plates, because everything in the parallel plates is simple because the electric field is a constant, just like with gravity. G, the acceleration due to gravity, is a constant. Okay, so for the parallel plates, this formula here, V is equal to this formula here, reduces to V is equal to QEH divided by Q. The Q's cancel, and you just get that V is equal to E times H. Okay, and so basically what this formula here is saying is that the further you go into the electric field, the more you go into the electric field, the more voltage you have. Or another way to think about it is the voltage is going to be equal to how big your electric field is multiplied by how far you've moved into it. Okay, I just put this in summary here because we actually are going to use these equations quite a bit, so I thought I'd just summarize them and put a little box around them. But basically, if you have an electric field and you multiply by how far you went into it, that's going to give you your voltage. And if you have your voltage and you multiply it by the charge that you put at that point, that's going to give you your potential energy. Okay, so what are the units of V? Okay, so the units of V using this formula right here. So if we take this formula here, which is basically the definition of V, all right, and we substitute in the units, you've got V is going to equal the units of energy divided by the units of Q. That's equal to joules per coulomb, okay? And a joule per coulomb is, by definition, a volt. All right, so there you go. So you know volts, like like a 12-volt battery or 1.5-volt battery, or electrical output is 120 volts. Okay, what that's telling you is that for every coulomb that flows out of that battery or that flows through that socket, it's being given so many joules. So like with a 12-volt battery, for every coulomb that flows out of that battery, it's delivered 12 joules of energy. Okay, so there you go. There's a 12-volt battery. Or a 9-volt battery, again, it would be 9 joules for every coulomb that flow out of the battery. All right, so it's not exactly an energy, it's an energy per unit charge that either flows out of the battery or that is at a particular point in space. Now, the next thing is the electric field now has come up in two formulas. One formula for the electric field was F is equal to QE, okay, which gave us the electric field as newtons per coulomb, okay, and we can actually see it right here, okay, newtons per coulomb. But now we've also seen an electric field in a different context. You've seen an electric field in terms of its potential, okay. Potential, voltage, they mean the same thing, so you'll hear me use both of those words, okay. So if you've got an electric field and you travel a certain distance into it, then you've gained so much voltage. And so an electric field can be written as volts divided by H, and voltage is measured in volts, and distance is measured in meters. And so another way to think of an electric field is that it's so many volts per meter. Okay, so you can either think of electric field as so many newtons per coulomb if you put a charge at a particular point in space, or it is so many volts per meter, okay, for how far you've actually displaced the charged particle into an electric field. All right, so now we can do a problem. All right. So what is the voltage at various points between two charged plates? Okay, and suppose the plates are charged such that there is a 1,000-volt potential difference between them. Okay, so here's what I'm asking. I've basically got these two electric plates here. So this one is positively charged and that one is negatively charged. Okay, now how did I charge them up such that there was a 1,000-volt difference in there? Well, basically you can do that by just attaching them to a battery. This symbol here, which you should see in the lab or will see in the lab, is basically a series of alternating long and short lines like that. This is basically the symbol for a battery, okay? And this particular battery is 1,000 volts. When I attach that battery to these parallel plates here, these metal plates, what the battery is going to do is it's going to suck electrons out of the positive plate and it's going to move them over to the negative plate. Okay, now it's going to continue doing that, but it can't do that forever because it gets harder and harder to pull to electrons out of the positive and deposit them into the negative. Think about it. An electron would want to be where the positives are, okay? And so the act of pulling an electron away from those positives and then putting them where the electron doesn't want to go, which is in this negative plate, that's going to take energy, okay? And so, the energy in displacing these, that's being delivered by this battery. Now, this continues until there's a potential difference between the two plates of 1,000 volts. Okay, and now what I want you to do is I want you to tell me what's the potential at various points in there. And so let's just scroll down here like that. And so here's my question. What is so this is A, that's like point A right there. What is the voltage in the middle of the two plates? Okay, so what's the voltage right in the middle of these two plates? All right, and then I also have a question. What is the voltage 2 centimeters from the negative plate? So there we are. I'm just trying to indicate here, that point B is 2 centimeters away from the negative plate. And then I didn't put C here, but I could ask the same question, like what is the voltage 2 centimeters away from the positive plate? Or I can ask what's the voltage at any point between these two plates. Okay, so how do you answer that? Well, the first thing is between those two parallel plates, there is an electric field. Okay, so the electric field is equal to V divided by H. Okay, and that's from above. And so it's 1,000 volts. in there divided by zero point 0.1 meters. And if you take 1,000 volts divided by zero point 0.1 meters, you get an electric field of 10,000 volts per meter. By the way, that's the exact same electric field that I had for that electron that was experiencing that acceleration at about 10 to the 15 meters per second squared. Okay, so there's 10,000 volts per meter. And so this is not hard to produce a 10,000 volt per meter electric field. All you need is 1,000 volts. This is easy to do in a lab with a power source. Okay, and you just put the two parallel plates 10 centimeters apart, and you've got a 10,000 volt per meter electric field. Okay, now again, if you look above, I did have 10,000. The magnitude of the electric field was 10,000, but there I had the units as newtons per coulomb. But don't forget that a newton per coulomb is exactly the same as a volt per meter. Okay, they're both totally legitimate units for electric field. Okay, now that's the electric field in here, and it's a constant throughout here. It's always 10,000 volts per meter. Okay, and now the question was, what is the voltage at various points? Well, actually, to answer that and to make it more intuitive, rather than doing it in MKS units, I decided, what's the electric field but in per centimeters? And so another, not another way, but using centimeters, E is going to be 1,000 volts for 10 centimeters, and so that's 100 volts per centimeter. And so the way to think about this is over here. The distance in here is 10 centimeters. As you move from the positive plate to the negative plate, okay, or actually from the negative plate to the positive plate. So if you're a positive charge, you want to sit here. If you want to sit here, you basically have no energy. And for every centimeter that you move towards the positive plate, you're gaining 1,000 volts. Okay, sorry, 100 volts. And so 1 centimeter in, 100 volts. 2 centimeter in, 200 volts. 3 centimeters in, 300 volts. 4 centimeters in, 400 volts. 5 centimeters in, 500 volts, and so on, all the way until you get to 1,000 volts. Okay, and so now it becomes pretty easy to answer the question, because if you're halfway between the two plates, well, let me scroll down a little bit more. If you're halfway between the two plates, okay, then you're at 500 volts. Okay, and if you're 2 centimeters away from the negative plate, then you're at 200 volts. Okay, because you'd be at 0 volts there. Always think in terms of a positive charge. A positive charge would want to sit right there. Okay, that's where this positive charge would want to be. And so over here, it's like you've pulled it into the field, 200 volts. Okay, if you pull it to the halfway point, that's going to be 500 volts. If you pull it all the way so that it's 2 centimeters from the positive plate, then it's 8 centimeters from the negative plate, and you're at 800 volts. If you pull it all the way to the positive plate, then you've gone the full 1,000 volts. Okay, so now you can see that the way this this is working is that the voltage basically grows linearly as you move from the negative plate to the positive plate, and the electric field is basically a constant pointing from the positive plate to the negative plate, and it's a constant. It shows the direction in which the voltage decreases. It decreases 1,000 volts for every centimeters. Sorry, 100 volts for every centimeters that you travel from the positive to the negative plate. Okay, so this actually leads to a very nice analogy, and you've actually heard me talk about the potential as potential difference or a potential drop. You'll hear people talking about this as a potential drop, and the reason is that you can actually think of potential as kind of like a height. Okay, and a positive charge would want to go from a high point, from high up to low. Okay, and so the potential is kind of like how high the positive charge is above the low plate, and the electric field is kind of like the slope of the hill. Okay, so let's look at this picture here and see how that analogy works out. So over here, if you have a positive charge here, that's like it's up high on the hill, and it wants to roll all the way down here to the negative. Okay, so if it's only halfway up the hill, then it's only at half the maximum voltage. If it's up at 80% of the height, then it's 80% of the full voltage, which is 800 volts. And if it's over here, it's not that high off the above the negative plate, and so it's only at 200 volts. And E is kind of like the slope. It's kind of like saying, well, how much do you drop for every centimeter of distance that you travel from one to the other, okay? And this is saying that you drop 100 volts for every centimeter, okay? And so people tend to think about voltage as kind of like the electrical equivalent of height, and they tend to think about the electric field as kind of like the electrical equivalent of a slope, okay? If you were to bring these two plates closer together, say they were only 1 centimeter apart, but they're still charged at up to 1,000 volts, well, then you would have not a drop of 100 volts per centimeter, but you would have a drop of 1,000 volts per centimeter, okay? So here's 1,000 volts between these two plates, and they're only a centimeter apart, so now you'd be dropping 1,000 volts between them. So now it's much steeper. The electric field would be 1,000 volts per centimeter. It's a much steeper drop. Okay, so I don't know if that helps or not, but this is basically the way people tend to think about potential and electric fields. They're very much related to one another. And I don't know if you've ever studied cartography, but in cartography, they often draw maps with the heights. They're kind of like these circular lines that show equal heights. Okay, and there's an equivalent of that in electricity where you can draw lines of equal potential. Okay, and these equal potential lines kind of, show the height. And whenever the equal potential lines are close to one another, that's where the hill is steepest. Okay. All right, so I don't want to go too far into that analogy. I hope it helps a little bit to give you an intuitive sense into what electric field and potential are. Okay, so let's do a problem, because we can do a problem now with this information. We have these two plates. They're 10 centimeters apart, and we charge them to 1,000 volts. Okay, and we place an electron 7 centimeters from the positive plate and release it from rest. Okay, so we have this electron. We place it into the um, electric field, and we release it from rest. Okay, and it's 7 centimeters from the positive plate. Now, I purposely picked a negative charge because we've been working with positive charges a lot. So now I want to think in terms of the negative charge. If this were a positive charge, it'd want to go to the negative plate, but no, this is a negative charge, so things are flipped. It wants to go away from the negative plate here, and it wants to go towards the positive plate. So what you want to think about is how far is the electric charge from the positive plate, and it's 7 centimeters. Okay, not to be tricky, but if I said, the charge is 3 centimeters from the negative plate, you wouldn't be using that in your problems. You wouldn't be using h is equal to 3. You'd actually be using h is equal to 7. You want to think, where does this negative charge want to go? This negative charge wants to go to the positive plate. How far is it traveling? 7 centimeters. Okay, so that's important. Like I could give you protons, or I can give you electrons on a test, or in the assignments. I think I have protons. And so when you've got the protons, they're positively charged. This entire diagram is flipped. Okay, so the protons would want to go with the electric field. The electrons want to go against the electric field. Okay, you can think of them as falling uphill. Okay, because they're negatives. Okay, all right, so the question now is, from there to there, what's the potential difference? Okay, so you've got the electron there, and it's going to go to the positive plate. What's the potential difference? Well, from above, the potential difference, V, is equal to EH. Okay, so you've got the electric field times the distance. Now, we don't want to go all the way across because the electron isn't traveling the full distance. The electron is only going to travel 7 centimeters. And so the electric field, we just found that it's 100 volts for every centimeter, and it's going to travel 7 centimeters. So the potential difference for this that this electron is going to experience is 700 volts. Okay, so I know that this is 0 there, and it's 1,000 there, but over here you could think of that as being like 3 centimeters from there. So this is like at 300. So if I were to draw, like I could have drawn here 300 volts, and it's going to go from 300 volts to the 1,000 volts. That's a difference of 700 volts. Okay, so now I asked for the velocity. Okay, so I'm going to be releasing this electron from here, and I said, how fast does the electron slam into the positive plate? And whoops, scroll down here. Okay, for the speed, we want to get the energies, because we'll actually be able to get the kinetic energy, and from the kinetic energy you can get the velocity. So the potential energy associated with that potential difference is given by this formula: U is equal to Q times V. Okay, and so we have that Q, this is the charge of one electron, is 1.6 times 10 to the minus 19 coulombs. Again, I'm not worried about the negative sign, because the negative sign is really all about the direction, and we've already taken care of the direction. We've analyzed that already. So it's just going to be 1.6 times 10 to the minus 19 coulombs. And the voltage here, the potential difference between where the electron starts and where it ends, is 700 volts. But notice that I wrote it as joules per coulomb. And you can see here, because that's the definition of a volt, is joules per coulomb. You can see here that the coulombs would cancel. And you're going to find that this is going to give you 1.12 times 10 to the minus 16 joules. Okay, so that's the potential energy of the electron when it's sitting right here. Okay, so when the electron is sitting right there, all the energy is potential. And I even said in the problem that I release it from rest. Okay, so I'm not giving the electron any kind of a kick, any kind of an initial velocity, because that would be extra energy on top of the potential energy. No, I'm releasing it from rest. So at this point, all the energy is potential. It's all potential energy. Okay, and we found that that is equal to, it's equal to this 1.12 times 10 to the minus 16. Now, what's going to happen is when you release that electron, it's going to speed up, speed up, speed up, speed up. It's going to be losing potential energy, and it's going to be gaining kinetic energy. Once again, that hill analogy that I gave you earlier, where you think of that 700 volts as kind of like a drop. Think of this as like a roller coaster, okay? And this electron is going downhill 700 volts, okay? And so it's dropping 700 volts from there to there. Well, at the top of the hill, it had all potential energy, and then when it gets to the bottom, all that potential energy is going to be converted to kinetic energy. Okay, and so the kinetic energy is going to equal the potential energy. Okay, so all of that energy is going to be converted to kinetic, and kinetic is calculated with 1/2 mv squared, like that. And so the potential energy, we worked that out already. It's 1.12 times 10 to the minus 16. Okay, joules, and that's going to equal 1/2. And now you need the mass of the electron, okay, which I gave you above. It's 9.11 times 10 to the minus 31 kilograms, and we've got v squared here. Okay, so just working out v squared, okay, is just a little bit of arithmetic in there. You find that v is equal to 1.57 times 10 to the 7 meters per second. Okay, now never in a physics problem, never just come up with a number and just write it down. Think about, does it make sense? And it's kind of hard to recognize whether this makes sense or not, because this is huge. This is a big number. Okay, why is it a big number? Well, because an electron is very, very light. Okay, and so the only thing we can really compare that speed to is the speed of light, the fastest known speed in the universe. Nothing travels faster than the speed of light in a vacuum. So the speed of light in a vacuum is 3 times 10 to the 8 meters per second. All right, and this is 1.57 times 10 to the 7 meters per second. So roughly speaking, okay, this electron is traveling at 5% the speed of light. All right, and so that is very, very fast. And you might wonder, well, is that possible? Can you really get to like 5% or some fraction of the speed of light in the lab? And the answer is yes, you can. Okay, now one thing I didn't mention is if you were to do this as an experiment, you might wonder, how in the world can I do this? Well, yeah, you can do it this way. Okay, you could have these plates and you can charge them up using 1,000 volts. Easy to do. With a power supply in a lab. 1,000 volts is not that much. Okay, these parallel plates would have to be 10 centimeters apart. All right, and you'd have to have the whole thing in a vacuum, because electrons won't travel very far before they get stuck to an air molecule or something like that. Okay, and so of course then they wouldn't hit the plate. And then for your source of electrons, you could just simply boil them off of like a tungsten filament, like a little light bulb filament in there, and these electrons would then just like literally pop off the surface of the material with not that much energy. And as soon as they feel the electric field between these the two parallel plates there, they would start to speed up and then slam into the positive plate. And by the time they're slamming into that positive plate, okay, even though they've only traveled 7 centimeters, because electrons are that light, they will have acquired a speed of 5% of the speed of light. So yeah, that is pretty fast. It is doable in the lab. In fact, not only was this doable in the lab, this was done every day in common households when we used to have the old CRT, the cathode ray tube televisions. Okay, these were the big